Okay, upon request, I want to talk about this particular problem, which involves rate in and rate out. So it's a rate in and rate out problem, and it's in 2005, number 2. This is I want to show you that this is looks complicated, but in fact it's a very simple problem. First of all, 2005, number 2. Number 2 indicates that you can use graphing calculator. And so you really want to be able to take advantage of graphing calculator functions that can save you lots of time. And we start out, let's read this, and I will make this available on the Veraclass so that, and also on the video, so that you will be able to see this problem as well. Here it says the tide removes sand from Sandy Point Beach from the rate modeled by this function r of t. So this is a rate of sand being removed from the beach, and it's equal to 2 plus 5 sine 4 pi t over 25. Now there's another function that's given to us here. Is a pumping station adds sand with this rate, which is 15t over 1 plus 3t. Okay, now both r of t and s of t are in the units of cubic yards per hour. So these are rate of change, and is measured from 0 to 6 hours. Okay, and at time equal to 0, you got 2,500 cubic yards of sand. Now this is very important. These informations are very important. First one is the domain, which these two functions actually have infinite domain. So this one restrained these functions, helping you to narrow your analysis. Second one is the initial condition. This is very important. This is talking about initially how much do we have. So by drawing from these two pieces of information on rate of change, later on we're able to find out the actual amount, but we have to always consider the initial condition. So let's take a look at part A. Part A says, how much sand would the tide remove from the beach during the 6-hour period? Now, the question asks for the actual amount of sand, but the actual amount of sand being removed. But we have the removal rate. So going from rate of change to actual amounts, we have to use definite integral. So the definite integral is employed right here, going from 0 to 6 r of t dt. Now you can write it out like this, or you can write it out with the actual equation. Now, this is very simple. Then you can take this and you can put this into your your calculator. Make sure it's in radian mode. Make sure all the parentheses are in the right place. Okay, so you can put it in y1 using this equation. Just put it in there in your calculator, and you can use the second trace buttons in your calculator and select f of x dx, integral f of x dx, and this should give you the answer. It should give you a numerical answer very simply, 31.815, and the problem asks you to indicate the unit of measure, so you will say this is cubic yards. So that's part A. Very, very simple. Yeah. So part B. So part A is the actual amount of sand being removed from the sandy beach, Sandy Point Beach, during the 6-hour period, right? By integrating the definite integral of the removal rate from 0 to 6. Okay. Now part B says write an expression of y of t. Now y of t. So they say we want to come up with this y of t, and this expression of y of t, and what is this? And this is the total number of cubic yards of sand at a given time. Now, in order to get this, well, first of all, we need to understand the rate of change. The actual rate of change for the sand, the amount of sand on the beach, should be rate in minus rate out. What that means is the actual rate of change for the sand is equal to the rate in which the sand being added subtract the sand that's being removed. Rate in minus rate out. So if rate in minus rate out is S of t minus R of t, right? Rate in, rate out. Rate in minus rate out. This will give you the actual rate of change. But the actual rate of change is still rate of change. We want the actual amount of sand over the 6 period, not over, at a given time. So if we take this rate and we take the antiderivative of this rate, it's actually integral from 0 to the time t. So we're taking the definite integral going from 0 to time t. That will give us the change of amount of sand, the actual amount of sand being added or subtracted, whatever the change that is, from 0 to some time away from 0. Now you say, is this then equal to the actual amount of sand? No, because this is the actual change in the amount of sand. That has to be added to the original amount of sand. So you must add it to the 2,500 cubic yards that was given to the original, that was the original amount that was given to us. And so then this is the equation. Let's review a little bit. Rate in minus rate out is the actual rate of change of sand. By integrating from 0 to t, this tells us that this is the actual amount of the change in the amount of sand. The actual change in the amount of sand. That change gets added to the initial amount, give you the actual amount of sand in a given amount of time, or at a given time. Okay, so that's part B. Part C. Now here it says we want to find a rate at which the total amount of sand is changing at t equal to 4. Find the rate. Find the rate. Now, if this is the actual amount of sand, the rate of change is sand, right? And so this problem sort of, in a sense, is going backward. We should have done this problem first. But this, we have to do whatever they're telling us. So in this case, this is y prime of t. So this is the actual rate of change of sand. And we just established earlier the rate of change of sand, the actual amount of sand on the beach is the rate in minus the rate out. And that's not simple. That's not simple. And that's it. That's the equation. And the equation is given, S of t is given by this, and R of t is given by that. So we can say that this is equal to 15t over 1 plus 3t minus parenthesis 2 plus 5 sine 4 pi t over 25. So we want to find out what the rate is at t equal to 4. T equal to 4. Now what that means is what's y prime 4? Well, that's easy, right? By putting 4 into all the t's, and then use your calculator to figure that out. Your answer should give you negative 1.908 cubic yards per hour. So that means that at that very moment, you're losing sand. Okay? Anyway, so that's what we have so far. Now, part D says from 0 to 6, from time equals from 0 to 6 in the 6 hour period, at what time t is the amount of sand on the beach reaches the minimum, and what is that minimum value, and justify your answer. Now, when you hear the word minimum in the context of a calculus problem, you know that it is about first derivative test. So I'm going to go ahead and erase parts of this so I have enough room to work out part D. So part D is asking for minimum. So we know that this has to do with the first derivative test of the actual amount of y of t. So we gotta take y prime of t. Y prime of t. Now notice, y prime of t was s of t minus r of t. S of t minus r of t. And the first derivative test, we had to take the y prime and we had to set it equal to 0. Now we don't have y prime of t, but we have s of t minus r of t. It's given to us right here at the beginning of the problem. So we can say, so then we want to set it equal to 0, and we have to find the critical points in which it will make s of t minus r of t equal to 0. Now how do we do that? Well, several ways you can do. You know that s of t is 15t over 1 plus 3t. So I'm going to go ahead and erase this portion so I have enough room to explain. Subtract 2 plus 5 sine 4 pi t over 25. And you want to set that equal to 0. A couple of ways you can do. You can set this as y1, right? You can set this as y1 in your calculator. You can just write it out. So if I will write this out, I will write 15t divided by parenthesis 1 plus 3t, parenthesis minus parenthesis 2 plus 5 sine parenthesis 4 pi x. In fact, on the calculator you only get x, so you won't get t. X right here. 4 pi x slash 25 parenthesis. Okay? So this is what you have for y1. And you can try to graph it. But make sure that your domain is between 0 and 6. Your domain is between 0 and 6. And then you can graph it and you can tweak the range a little bit so that it will show up. And then you can use a second trace button right here in your calculator and select 0. The function that will find zeros. Because on your graph, you will be able to see where this hit the x-axis, right, between 0 and 6. This should give you, at least according to my my value here, a should give you or x. It should give you a critical point at 5.11, something close to that. So what you can do, you can use the first derivative test at 5.11. Now, granted, maybe there's some other zero somewhere else, but notice our domain is only from 0 to 6. So between 0 and 6, right, between 0 and 6, that's my critical point. So I'm not going to write 0 and 6 right here. But this is where my x is, and this is where my y prime is. And at 5.11, my y prime is equal to 0. And you take a value smaller than 5.11, maybe 1, and you can put it into y prime, and you should get a negative value. Okay, you should get a negative value. It comes down like this. this way, and you take a value that's bigger than 5.11, maybe 5.5, you should get a positive value. It goes like that. So what that means is at t equal to 5.11, y of t, the actual amount of sand, is at maximum. Okay, at maximum. Now you remember, and so the question is, okay, so that if that's the case, that's the answer. But that's not the only answer they ask for. They're asking for then what is the minimum, oh I'm sorry, this should be minimum, not maximum. Minimum is at minimum. But what is the actual minimum value? This 5.11 is not the minimum value. 5.11 is when the minimum value will occur. But what is the actual minimum value? So I will need to erase these just to, in order to make room for us to figure that out. You remember earlier, we figured out that y of t, this was from part B, from B, we say y of t is equal to the integral from 0 to t, okay, from 0 to t, s of t minus r of t dt, and then we will add to the initial amount in the sand, on the beach, initial amount of sand on the beach, 2,500. So then if I want to find out what y of 5.11, then I will go ahead and just use this equation, 0 to 5.11, and s of t, now you have this in your calculator, or at least you kept it if you did, and you can just use this in your calculator, and it should come out to be 2492.3 cubic yards, and that will be your answer, and this is the equation that you will use. Okay? In sum, this problem has to do with rate in and rate out. If we are talking about the actual amount of the sand on the beach, it will be the integral of the rate. Now, if it's talking about the actual amount of sand, the total amount of sand at a given time, then you are taking the definite integral of the rate, which is the rate in minus rate out, plus the initial condition.